Hi, this is Mrs. Westmoreland, and this is a video on photoelectron spectroscopy, which is really the last piece of experimental evidence that we're going to use to justify the atomic models. So by the end of this webcast, you should be able to understand how PES can be used to probe the electronic structure of atoms, and also how the data confirms the shell and subshell model of the atom. So photoelectron spectroscopy, which is abbreviated PES, is a powerful tool that we use to probe the electronic structure of naturally occurring elements as well as mixtures of elements. You'll definitely want to be sure that you've watched the video on photoelectric effect before going any further, because much of this data derives from the photoelectric effect. So we know from this equation, energy is equal to Planck's constant times frequency, that we can use electromagnetic radiation to investigate atoms. And so some of the ways we do that are with infrared radiation and molecular vibrations, visible light, certainly for some of those electron transitions in the Bohr model. As the electrons return to their ground state, they might emit photons in visible light. And also certainly also those are in ultraviolet range transitions. So in photoelectron spectroscopy, we need energy to be able to remove not only valence electrons, which is from the ionization energy data, but also we will be removing electrons from the core. So valence electrons, ionization energy will usually fall in the ultraviolet range. But for core electrons, we're going to need a greater energy, a higher frequency, and that's more going to be in the X-ray range. And so as long as we have enough energy to remove core electron, we should also have enough energy to remove the valence electrons. And so much of these core electrons, and this is just an equation using experimental data, much of those core electrons will require X-ray radiation. So the energy that is provided in PES is usually UV or X-rays. So this last equation on this slide is important for PES, because whatever energy that we provide to the sample of matter, which is the H times the nu, is going to be equal to not only the ionization energy that is required to remove the electron, but then the kinetic energy of those electrons once they have been removed, by that idea of the photoelectric effect. And so by analyzing the kinetic energy and sort of subtracting out the energy required for ionization energy, we can make some conclusions about the structure of the atoms. So this is just a picture of a PES instrument. Mostly can't really tell what's going on in there. So we've just got a vacuum chamber where we are providing UV and X-ray radiation, and then detecting what's coming out of the samples of matter. So kind of a particle level diagram of what's going on is that we have an X-ray or a UV source, and here we have some atoms of lithium. So we're going to provide the energy, and that's going to remove electrons, and we're going to analyze by looking at the kinetic energy of those electrons that are coming off, how much ionization energy it took to remove them. And you can see sort of in this metallic bonding structure that the valence electrons are free to move between atoms, and so we've got some transitions between atoms. And you've got the detector up at the top, which is creating these peaks. So the important information in that previous slide is that we have two different peaks that are really going to represent the two different shells in which we find the electron. So the one that requires less energy to remove is the one that's in that valence shell, and the one that requires more energy to remove are the ones that are in that more core shell. And you can also see that the relative size of the peaks gives you an idea of how many electrons there are with each of those energies. So in this atom of lithium, we have one in the second shell and a larger peak to represent the two electrons that are in that core shell. So here's another example of boron. We've got 5 protons, 2 electrons in the first shell, and 3 electrons in the second shell. So we've run the simulation. The X-ray or UV source causes the electrons to be removed. By analyzing the kinetic energy of those electrons, we can then subtract out the kinetic energy and figure out how much energy it took to remove the electrons. And so we are seeing these peaks that represent essentially the ionization energy. So now you'll notice that with boron, even though it has only 2 shells, we have 3 peaks. And that's where we're going to be starting to analyze the subshells, in that the electrons that are in the third shell do not all take the same amount of energy to remove. So these would be the first shell electrons, the core electrons that take the most amount of energy to remove. And then of those 3 electrons in the second shell, 2 of them take about the same amount of energy and 1 takes less energy. And so this is the data we're going to be looking at to sort of support the idea of subshells in the electrons, the PES data. So lithium had just 2 peaks. Boron has 3, 2 of them much closer to each other than the other. So here's some data that you might be asked in an AP question. We can see this first higher energy peak, which would represent the 1s electrons. The next peak, same height, would represent the 2s electrons. And then the next one of slightly less energy to remove, which is taller, would represent the 2p electrons. And so by analyzing the position of the peaks and the height of the peaks, we can make a prediction about what element we might have here. And in this case, since the height of the 2p electron peak is 6, whereas the height of the 2s electron is 2, we can make a prediction that this is most likely neon with an electron arrangement of 1s2, 2s2, 2p6. Here's one more. Again, we're going to identify the element and its electron configuration from the PES data. And so we can see a peak at 151, which would be the 1s, 2, a peak at 12.1, which would be the 2s2, peak at 7.9, which would be the 2p6, a peak at 1.09, which would be the 3s2, and then a peak at 0.58, which would be the 3p1. And so based on the location of the peaks and the height of the peaks, we can predict that this particular spectrum would belong to aluminum. That's all for now. We'll do some more sample questions in class. I hope this helped, and thank you for listening.